Okay, so hello and welcome everyone to week 8 of interactive live sessions for the course on fundamentals of convective heat transfer. The course is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras and I'm a TA for this course, and like every other week we shall be solving sample problems together. So this during the lectures of week 8, we stopped discussing on forced convection and you know focused our attention on natural convection, which is again a very important aspect of studying convective heat transfer because in most naturally occurring cases, there is no force, there is no external force. It's just the buoyancy differences which drive the flows. Let it be, the geostrophic flows around the Earth, which causes, different weather states as we experience. Then, on a smaller scale, we have the heating and cooling of different substances, subjected to a uh, ambient at a different temperature. It could be our own bodies in a hot or cold temperature, or it could be something else. It could be some hot cup of tea which we want to cool down in a colder ambience. So in many engineering aspects also where there is no external forcing to cool, there also natural convection comes into play. So it's no doubt a very important topic to learn about, and we shall be discussing questions relating to that topic itself. So without any further ado, we will jump into the questions. So this is our question number 1 for today's session, which is asking us that Grashof number. We learned about this number during our lectures of week 8, and what is this is a non-dimensional number. The question is asking what is Grashof number a measure of? Is it the ratio of option A, inertia force to viscous force, option B, buoyancy force to viscous force, option C, inertia force to surface tension, or is it D, buoyancy force to inertia force? So what will it be? Read the question carefully first, then try to figure out the solution. And once you have figured out the answer, you can either type it in the chat box or you can unmute and answer. However, you feel comfortable, please go ahead. And if you want to ask anything or clarify anything regarding the question or anything surrounding the question, please feel free to ask. Please don't hesitate. Okay. So we have one quick response in favor of option B. Let's see what others have to say. One more option B. So for the people who are joining now, we just got started with the first question of today's session. Uh, this is asking us that Grashof number, the non-dimensional number which often appears in the governing equations of natural convection. What is that Grashof number a measure of? Is it the ratio of option A, the inertia force to viscous force, option B, buoyancy force to viscous force, option C, inertia force to surface tension, or is it option D, buoyancy force to inertia force? And option B seems to be the popular choice among everyone. We have got 3 responses so far in favor of option B. Okay, so let's have a look at the correct solution then. And the solution is indeed option B. So those of you who responded, well done, you responded correctly. Grashof number indeed is a measure of the buoyancy force to the viscous force. So if we look at Grashof number, with respect to some length scale h. It's given by g beta delta t h cube divided by some u ref any reference velocity squared. Right? So this is what corresponds to the inertial forces, and the numerator this corresponds to, so this is inertial force, and this is like the buoyancy force. Okay, this should be viscous forces, right? Did I do this correctly? So I'll quickly have a look at what Grashof number is. Maybe I'm making some mistake here. So yeah, oh okay, sorry. It's not u, rather it's mu squared. So this is what represents the inertial force, and the numerator that represents buoyancy forces. So that's how Grashof number ends up being a measure of the ratio of the buoyancy force to the inertial force. So what it means in real life. So in a practical situation, if this Grashof number is greater than 1, then that means it would be a buoyancy driven flow. And if Grashof number is less than 1, then that would mean that sorry, I should correct this as well. This is not inertial, but rather viscous forces. So that means that viscous forces would dominate. Okay. So any questions regarding this? Okay. So if there are no questions, we will keep moving. We will move on to question number 2 now. Now, question number 2 is asking us, what is the relationship between the upward velocity of a fluid and the distance from the bottom of the plate when the plate is hotter than the fluid? So, what I mean by this question is, I have a plate like this, and from the bottom of the plate I'm measuring this distance y, let's say, and the as I go farther away from the plate, that's x. And so the question is, and another thing is that the plate is hotter than the fluid. So I have, let's say, the fluid at some t infinity and the plate at some t wall, tw, which is greater than t infinity. So this is hotter. So what will happen? So the fluid close to it would absorb heat. It will get lighter and it will try to move up. So that will create a boundary layer like this, as we have already seen. So there will be a velocity profile set up resembling something like this. It will go down, and similarly there will be a temperature variation as well. Anyway, so what it means is that, so what is the relationship between the upward velocity of the fluid? So this is, let's say, some v with which it's going up, and the distance from the bottom of the plate. So this is v and this is y. So what this question is asking us, what is the relationship between the velocity v and the distance from the bottom of the plate y? So option A says that as the distance from the bottom of the plate increases, the upward velocity of the fluid near the plate surface decreases. Option B says, as the distance from the bottom of the plate increases, the upward velocity near the plate surface increases. And option C is the upward velocity of near the plate surface is small all over the plate. It does not vary. And option D says that it's unpredictable. It could be anything. So what is it among the four options? We have two responses in the chat box in favor of option A. Let's see what others have to say. So what is the relationship between V and Y? We have two responses in favor of option A. Let's see what others have to say. So does V increase with Y? Does it decrease with Y? Is it unpredictable? Or is it so small that it doesn't matter? We have question number 2 of today's session over here, asking us that what is the relationship between the upward velocity of the fluid and the distance from the bottom of the plate when the plate is hotter than the fluid. So as distance from the bottom of the plate increases, the upward velocity of the fluid near the plate surface decreases. Or option B, as the distance from the bottom of the plate increases, the upward velocity of the fluid near the plate surface increases. Or is it option C, that the upward velocity near the plate surface is small all over the plate? Or is it option D, unpredictable? There are some mistakes over here. So the upward velocity, uh, it could be just near the plate surface, is small all over the plate. So let's have a look at the solution. The solution is actually option B. As the distance from the bottom of the plate increases, the upward velocity of the fluid near the plate surface increases. So if you remember properly, so for low Prandtl numbers, this velocity was proportional to y to the power 1/4, and for higher Prandtl numbers, this became proportional to y to the power 1/5. Now, in both these cases, with increasing y, meaning the distance from the bottom of the plate increasing, the velocity also increases. It's not a directly proportional thing. There's an index over here of 1/4 or 1/5, but nonetheless, with increasing distance, the velocity also increases. So that's why it would be option B, not option A. Is everyone convinced? Any questions regarding this? No? So we will keep going forward. We will now move on to question number 3. It's a very simple question. For high parental fluids and natural convection over a vertical isothermal wall, that is, this wall is sorry, this wall is maintained at a constant wall temperature Tw. I have a Prandtl number much higher than 1, and there is natural convection going on. Now, as you know, there will be two boundary layers set up here, one thermal boundary layer and one hydrodynamic boundary layer. So those boundary layers, they will have thicknesses delta and delta T respectively. So delta is for the hydrodynamic boundary layer, and delta T is the thermal boundary layer thickness. So it's thickness for both. Now the question is, what would be the relationship between this delta and delta T? Would option A, delta be much greater than delta T? Option B, delta be much less than delta T? Or is it option C, that delta would be, uh, you know, of the order of delta T? They won't be very high or very lower than each other. They will be of comparable magnitudes. Who's this? Sorry. We have one quick response in favor of option A, that is delta would be much greater than delta T. Let's see what others have to say. Remember, the clue here is that it's a high Prandtl number fluid. We have one response so far in favor of option A, telling us that the hydrodynamic boundary layer thickness would be much higher than the thermal boundary layer thickness. There's a additional clue over here, that is this Prandtl number is much greater than 1. Now since Prandtl number is equal to nu by alpha, this would mean that nu is much greater than alpha. Now what do you think? Okay, we have a few more responses, two more responses in favor of option A. Okay, now let's have a look at the solution. And all of you are correct. So option A is the right answer. That, and the clue remains over there, that since Prandtl number is much greater than 1, this means that the momentum diffusivity is much greater than the thermal diffusivity, meaning that momentum would diffuse further than the uh, than heat. So that's why I'm trying to change my color over here. Another pen. This is my wall at TW. This distance is delta T, and this one is delta. So since this nu is much greater than alpha, this delta would be much greater than delta T. So if I draw the profiles now, the temperature difference would die down slowly, this being, let's say, delta T. And this is our x along this distance. And on the other hand, this velocity would increase and then decrease at a much greater length. So this delta t would be much greater. No, sorry, delta would be much greater than delta t. That's why it's option A. Does that make things clear? Any questions regarding this? Okay, so if there are no questions, we'll move on to the next question, which is very similar, but let's say if it's similarly straightforward or not. So here we are asking that for low Prandtl number fluids and natural convection over a vertical isothermal wall, what is the case? Is it option A, delta much greater than delta T, option B, delta much less than delta T, or is it option C, delta comparable with delta T? So it's a very similar question, only this thing is reversed. It was a high Prandtl number fluid earlier. Now we are telling that it's a low Prandtl number fluid. What will be the case for this one? We have one quick response telling us that it's option B. Let's see what others have to say. Think carefully, and once you have arrived at the correct solution, you can put in your response in the chat box, or you can unmute and answer as well. In the previous case, where the Prandtl number was high, then we saw that the hydrodynamic boundary layer was much thicker than the thermal boundary layer. What will happen for a low Prandtl number fluid? Would it be option A, delta much greater than delta T, or option B, delta much less than delta T, or is it option C, delta comparable to delta T? We've got only one response so far. Let's see what others have to say. No need to hurry. Think through. You can even go back to your notes and lectures, but try to be very clear about the problem at hand. One response so far in favor of option B, telling us that delta T is much greater than delta. Okay, we have one more option B. Okay, what about the rest of you? What do you think? Does anyone think it will be not B but something else? Could it be something else? Anyone? Okay, let's have a look at the solution. So the solution is actually option C and not option B. Delta would be comparable to delta T. Now why is that? Because let's say we have a plate like this, and since our Prandtl number is much lower than 1, that would mean that our viscosity is much less than alpha. So you can imagine that at least delta won't be less than delta t. Sorry, at least delta t won't be less than delta because alpha is greater than nu. So let's draw the thermal boundary layer first. So I'm using blue ink to draw the thermal boundary layer, delta T. So this is up until where our temperature varies. So if I have a temperature difference like this, it takes this much time to die down. Now you have to remember what is the source of velocity over here. The source of velocity is that some pocket of fluid, it got heated up, and as a result its density went down. Therefore it experiences a buoyant force towards the upwards. So that causes it to move. That's what causes the velocity. So some temperature difference results in some velocity v. So in the entire region within the thermal boundary layer, the fluid gets heated up. Even by a little amount, it does get heated up. So, and that would result in an upward velocity. So, it's not that just because that alpha is much greater than nu, that delta also would be much less than delta t. Because wherever there is a temperature difference, there will be a velocity. So, if I now draw the velocity profile, it would be something like this, right? So every part of it inside would experience some upward buoyant force causing it to move. So there won't really be a difference in delta T and delta. They would be comparable. Get my point? But however, there is this small region near the plate where these velocity gradients are pretty huge. We call that delta V, or the viscous region, where viscous forces are very dominant. This delta V can be told that this is now much less than delta T. But the hydrodynamic boundary layer itself is comparable to the thermal boundary layer, because wherever there is a thermal effect, wherever the fluid got heated up even by a little bit, it will experience a buoyant force and it would try to move up. That's why option C would be the correct answer in this case. Get my point? So if we again try to draw a similar profile, so I'll have a velocity profile something like this, where there is a very high gradient in front, very near the wall, and with distance increasing from the wall, this it will have a gentle slope. This is what I call delta V, and this entire distance is what I call delta. And if we draw the thermal boundary layer, this will be something like this. This distance again we call delta T. This is X. So that's why delta would be comparable with delta T. Does that make things clear? Am I making sense here?
Yes, sir.
Questions, anyone? So this was a little bit tricky. I hope the answer is clear to everybody. If we, forget the physics and look directly into the math, then that may misguide us, telling that, the thermal diffusivity is so much higher than momentum diffusivity. So the thermal boundary layer should also be much, much greater than the viscous boundary layer, or, the hydrodynamic boundary layer. But that's not so. Okay, so if things are clear, we will keep on moving. We'll move on to question number 5, which is asking us about another important non-dimensional number. We learned about Grashof number earlier. We will now look at Business number and what is it given by. So it's the definition of Business number which is at stake here. So is it option A, Rayleigh number into Prandtl number? Is it option B, Rayleigh number divided by Prandtl number? Is it option C, Rayleigh number to the power 1/4? Or is it option D, Rayleigh number into Prandtl number to the power 1/4? We have one very quick response in favor of option A. Let's see what others have to say. Come on, no more responses? I would urge everyone to participate in these. Even if you have problems in typing in the chat box, you can unmute and answer as well. Sorry, unmute and answer as well. These are interactive sessions, so the more we can make these sessions in more interactive, the better. So Business number, is it given by option A, Rayleigh number into Prandtl number? Option B, Rayleigh number divided by Prandtl number? Is it option C, Rayleigh number to the power 1/4? Or is it option D, Rayleigh number into Prandtl number to the power 1/4? Alright, so let's have a look at the solution. It's a straightforward one. So it's option A, Rayleigh number into Prandtl number. So in the equations governing, natural convection, it's this combination of Rayleigh number and Prandtl number which often shows up, and this is what we define as Business number. So it's Rayleigh number with respect to some length scale h, and this is very important because this has a physical meaning as well, representing the ratio between the uh, buoyancy forces and the uh, viscous and inertial forces. So would it be a more buoyancy dominated flow, or a buoyancy dominated case, or a flow dominated case? That would be determined by this Business number. Alright, so if there are no questions regarding this, we will move on. We'll move on to question number 6. This is again about another important non-dimensional number known as the Richardson number. What is it given by? Is it option A, GR into PR? So over here, GR means Grashof number. Or is it option B, Grashof number divided by Reynolds number squared? Is it option C, Grashof number divided by Reynolds number? Or is it option D, Rayleigh number divided by Prandtl number? What would this be? Okay, we have one response in favor of option B. Let's see what others would like to say. So option B says that it's uh, Grashof number divided by Reynolds number squared. We have one more answer in favor of option B. What do the others have to say? Would you agree with option B, or would you like to say that it's something else? So what is Richardson number given by? Question number 6 of today's session. Is it option A, the product of Grashof number and Prandtl number? Option B, the ratio of Grashof number with Reynolds number squared? Is it option C, the ratio of Grashof number and Reynolds number directly? Or is it option D, the ratio of Rayleigh number and Prandtl number? Okay, so let's have a look at the solution. The solution is exactly option B. So those of you chose this option, you're correct. So this actually has a physical significance. So if Richardson number is much greater than 1, then that means that uh, in the system the buoyancy forces is much higher than the inertial forces, and as a result we can say that it's a natural convection case. The convective heat transfer by natural convection is much higher than any kind of forced convection that could take place. And if this Richardson number is much less than 1, then that means that inertial forces are much higher. And it would be better if we consider forced convection. So the natural convection going on over there would be very low. And Richardson number being comparable to 1 or of the order 1 would mean that both natural convection and forced convection are of similar orders of magnitude. So this makes our lives a bit more difficult, and we have to consider both, and so, such cases are known as mixed convection cases. So this Richardson number has a direct engineering application, that from the magnitude of the Richardson number, you can determine the tools to use to solve the problem, or the physics problem that we're dealing with. Is it a natural convection case or a forced convection case, or do I need to consider both? That is important. Okay. Any questions regarding this?
No, sir.
Okay. So if there are no questions, we will keep rolling. We will move on to question number 7, which is asking us that for natural convection on a vertical plate with uniform heat flux, what is the relationship between the thermal boundary layer thickness delta T and the distance from the bottom of the plate or the top of the plate, in case the plate is colder than the ambient fluid? So is it delta T proportional to y to the power 1/4? Is it option B, delta T proportional to y to the power 1/5? Is it option C, delta T proportional to y to the power minus 1 by 4, or is it option D, delta t is proportional to y to the power minus 1 by 5? Which one would it be? So for a hot plate where Tw is greater than T infinity, it would be something like this, where y goes this way and x goes this way. On the other hand, if I have a cold plate, let's say Tw is less than T infinity. So here what will happen? So here the fluid near the wall will lose heat, become denser, and start to sink down. So in this case, the boundary layer would be formed this way, and the velocities would be this way. So in this case, we will consider x in the same direction, but y would start from the top and go towards the bottom. So y equal to 0 basically means start of the boundary layer. So whichever way the boundary layer is oriented, we will orient our y accordingly. So the question is, how does this delta T vary if there is a uniform heat flux, that is this Q double prime is a constant? Okay, we have one response in favor of option B. Let's see what others have to say. One more response in favor of option B. We'll see what others would like to say. Okay, we will quickly have a look at the solution. We actually spoke about this earlier in one of the slides. So for an isothermal case, for an isothermal wall with Tw equal to constant, we have this delta T to be proportional to y to the power 1/4. And for a uniform heat flux case, where Qw double prime is equal to constant, in this case delta T becomes proportional to y to the power 1 by 5. So in a simple case like this, where y is this way and x is this way, this delta T would grow as the 1/5 power of y. So there will be a sharp increase when y is low, and this would become smoother and smoother as y increases. Okay, any questions?
No, sir.
So if there aren't any questions, we will move on to the last question of today's session. We are there pretty early today. So anyway, so we have a cylinder like this. This is a very practical problem. Pay attention here. So if I have a cylinder and I have to cool it, so it's a very practical problem. So let's say you bought a can of a beer, and but it's hot. You can't drink it that way. You have to place it in a freezer to bring the temperature down and chill it. So chilled beer always tastes better, right? So if you want to chill it, in you have to chill it in a hurry. So you don't have much time to do it. So in which orientation to put the can so that it gets cooled quicker? That's what essentially this question is asking us. So we have a cylinder here with a radius of 3 centimeter and a height of 30 centimeters. So the height is 10 times the radius. So it's a long slender can cylinder. So it has to be cooled by placing inside a refrigerator filled with cold ambient air. So the ambient air T infinity is lower than the surface temperature of this cylinder Ts. So in which orientation will you keep it in a vertical manner or will you keep it in a horizontal orientation? In which orientation do you think that it would get cooled much faster? Try to think about this intuitively. What do you feel? Would the vertical orientation cool it faster, or will the horizontal orientation cool it faster? Any guesses, anyone? Okay, we have one response telling us that it's the vertical. Say, okay, so vertical seems to be the official guess of this crowd. So two people have res- wrote in the chat box that the vertical cylinder will cool much faster. So to answer this in a very rigorous manner, so I pulled out this solution from the internet. So it's a very uh, detailed solution considering the Nusselt numbers for cylinders of different orientations. So let's say they took some corresponding length of this much and diameter this much. This does not match with our value, but nonetheless the nature of the math would remain the same. So here they found out what the uh, bulk, uh, what is it called? Forgot the name of it. The volumetric change with respect to temperature. What is it called? I forgot the name. The beta.
Beta, beta.
It's volume, but volumetric change rate. So whatever,
Bulk mean temperature.
compressibility, right? Yeah. No, no,
It is
not bulk.
volume expansion coefficient.
Volume expansion. Correct. So they found it out for the film temperature, which they took as the average of the ambient temperature and the surface temperature. Then they found out what the Rayleigh number would be over here. So found out what the Rayleigh number would be for, now this is the horizontal case. In this case, they found that the Rayleigh number would be 6.3 into 10 to the power minus 5 something. And for a horizontal cylinder oriented in this manner, the Nusselt number is equal to 0.48 into Rayleigh number to the power 0.25. This comes from some piece of work which someone must have done with horizontal cylinders. And now that gives us, after plugging in the value of Rayleigh number, this Nusselt number comes out to be 13.52. And similarly, the heat transfer coefficient turns out to be 5.19 in SI units, watt per meter cube Kelvin. Now, for the vertical case, the Rayleigh number comes out to be higher. So it's something into 10 to the power minus 6, which is, at least one order higher than the Rayleigh number for the horizontal case. But the Nusselt number for the vertical case, for a vertical cylinder oriented in this manner, the Nusselt number is related to the Rayleigh number and Prandtl number in this more complicated way. This comes from experiments. Now, after plugging in the values of Rayleigh number and Prandtl number, this is what the Nusselt number comes out to be, and simply we then find out what the heat transfer, the convective heat transfer coefficient would be, and this turns out to be 5.049. So if you now compare these two values, 5.18 and 5.049, you can see that this one is higher, right? The horizontal case. So in this particular case which they took, this came out to be 3% higher than the vertical case. Now, all this complicated math aside, if we just try to think of it from a physics perspective, so I have a cylinder like this, imagine. So I'm looking at the front view only, and the ambient fluid is at a lower temperature. So what happens is basically heat transfers from the cylinder to the ambient air. So a boundary layer like this would be set up, correct? So any packet of fluid which is over here, this got some heat from it, and this is only moving up, right? So there is very little temperature change that can occur if this length is much higher, because it's already, heated up. It can't absorb more heat from the cylinder, right? So, and on the other case, if I keep it face down like this, so you can imagine, right? This is the cylinder. I'm only looking at this part. Sorry. And erase the back and only look at, some sectional view sort of. So here also we will have boundary currents set up like this, and here also, particles of fluid would, take heat from this and move up. Now, this radius or even the diameter, we saw that this is, at least 10 times smaller than the length. So in our case, our radius was 3 and our length was 30 centimeters. So this is 30 centimeter, and d was equal to some 6 centimeters. So d is, less than or at least equal to, sorry. So our d is equal to L by 20. So it's much smaller than L, you can imagine. So in this case, this distance is lower, but the surface area is still the same. It's still, if you take the projected area, the projected will be some d into L for this case, and for the vertical case also, the projected area would still be the same. The projected area would still be order of dl, not exactly equal to dl, I'm telling order of d into L. So it's the same area available for heat transfer, but the fluid particles the colder fluid particles coming into contact with this hot cylinder is much more for the horizontal case because its height is lower, right? Does that make sense physically? So that's why putting it in a horizontal orientation would cool cylinders much faster. It would enhance the heat transfer rate by natural convection. Okay, good. So this brings us to the end of today's session. Uh, my questions are over. If you have any questions, shoot away.
Hello, sir.
Yeah, hello.
Sir, I have a question regarding the questions that will appear in the exams. What type of ratio can we imagine 70/30 related to that question, sir? What type of question we can in what ratio we can like
Ratio
what type of
between
ratio
what?
of questions, sir? Yeah,
No, I'm not
multiple
understanding.
choice and also different options, something like that. What type of question we
Okay,
have to?
so in the main exam, there will be subjective type of questions, and
Okay, sir.
our lecture is very much, as you have already experienced, is very much mathematical. There is a lot of analysis involved in it. But
Okay,
I think the weightage on derivations would not be too much. You won't be asked to derive this entire thing, but
okay, sir.
there will be, one thing I can say for sure that numerical problems will definitely be there. And very
That's what.
similar.
Yes, sir. Yes, sir. That's what I am asking, sir. What is the ratio for the subjective and also descriptive type? If there is anything, and
Uh,
also
I
numerical
don't
one.
think that's fixed. That keeps changing every year.
Ah, okay, sir. Okay, sir. Thank you, sir.
Anyway, there will be a mixture of both, and
Okay,
subjective questions will definitely be there. And
okay, sir.
within that, numerical type questions are, a must. So for at least 5 6 types of numerical problems that we discuss in the lectures as well as in these interactive sessions, uh,
Okay, sir.
won't be too different from that. So if you closely follow these questions which are being discussed, it
Okay,
shouldn't
sir.
be too much of a problem. Right?
Okay, sir. Thanks.
Okay. Okay then. Thank you. Bye bye. Good night. We'll meet again next week. Oh yeah, and happy Ganesh Chaturthi to everyone. It was
Yeah, thank you,
yesterday
sir.
in some
Same to you, sir.
parts and today in some parts of India. Okay.
Yes. Thank you, sir.
Thank you.
Thank you, sir. Good night.